Good morning, everybody. So today we're going to start treating the Debye model. Okay, I will remind you that we solved the Einstein model, and in Einstein model we compared the outcome of the Einstein model. Basically, the idea is what happens to a solid. Specifically, what happens to a specific heat of a solid. Okay, so if we have Cv as a function of temperature, right, we know that there are two universal limits. The low temperature regime, which goes up as the temperature to the third power, and the high temperature regime, which converges to a constant. And this constant, so if we divide it by the number or the size of the of the size of the system, or the number of the particles in the system, this constant, it is 3K Boltzmann. 3K Boltzmann. Okay. Now, this part was very well explained by the Einstein model. But the Einstein model failed to describe the low temperature behavior. Okay. Now, what were the assumptions of the Einstein model? The assumptions of the Einstein model were, we have a system, it's composed out of particles that somehow fixed to specific locations, let's call them atoms. Okay. And all those atoms can perform oscillations as harmonic oscillators in 3 different directions. So each particle have 3 degrees of freedom. On total we have n particles, and we treat them as independent harmonic oscillators. That was the Einstein idea. Moreover, Einstein said the following thing: all the different particles, because they are identical, have exactly the same omega, have exactly the same frequency. Okay? So the energy of each of the particle, EI, so this is the energy of particle number I, is n h bar omega. And all of them have exactly the same omega. Now that was a problem, because maybe they are not identical, etc., etc. So anyhow, we have shown that those ideas work extremely well, high temperatures, not so well, low temperatures. So where can be the problem? And this is where Debye enters, and he suggests the following corrections to the Einstein model. So first of all, Debye says, well, if we think about it, what we know about solids? So we know about solids that there are waves inside solids, right? So you had a class on waves. So in each solid, there is a specific type of propagations of waves. Sound waves, for example, or some other kinds of waves. Basically, local vibrations inside the system. Now, what is a wave? So we know that there can be standing waves inside any solid. Now, what are those waves? Those waves are not independent vibrations of the different particles. Those waves are cooperative vibrations. So what Debye said is that, well, it's very nice, Professor Einstein, but we know that the different particles inside the system, at least from the perspective of the wave theory, the different particles inside the system are not independent. They move in a cohort. They move together. They oscillate together. Meaning there are strong correlations and strong dependence between the motion of that particle and this particle. And maybe they are moving together. And then can be other correlations between this particle and that particle. Basically, the assumption of Einstein is simply not true because all the particles are not independent. Somehow it works out in the high temperature limit, but well, maybe in high temperature limit they indeed do not care about each other. But because what is high temperature? High temperature is high kinetic energy. Okay, so you learn from thermodynamics that kinetic energy is proportional to K boson T. So high temperature, high kinetic energy. High kinetic energy, I don't care about the interactions with my neighbors, I don't care about the interactions with anybody else, so I can indeed be independent. So this is maybe why Einstein's theory works so well for high temperatures. But with low temperatures, interactions with the neighbors become important. Particles are not independent. Okay? And maybe they're even not harmonic oscillators anymore. Who knows? So, two main problems, according to Debye. One, we don't really know if they are harmonic oscillators. Two, all the different particles are not independent. Okay. Now, this can be formulated rather very nicely if we think about the general Hamiltonian of the system. So let's see how a general Hamiltonian of a system looks and how we can basically present it such that maybe it can represent a harmonic oscillator representation of the system. Okay? So I still want just to explain why the picture of Einstein breaks down. And I'm going to show it by using the Hamiltonian of the system. Okay, so what is the Hamiltonian of the system? Any questions? No. So what is the Hamiltonian of the system? Let's use new markers. So the Hamiltonian of the system is just 1/2. I'm saying the following. Let's write first thing first. Let's write down the kinetic energy. Okay. So we're going from J equals 1 to N. So J is the number of particles. And we are also summing for each J on I equals 1, it's the X direction. I equals 2 is the Y direction. And I equals 3 is the Z direction. So I goes from 1 to 3. Of X, Xj, I dot square. Okay. So I do still assume that all the different particles are the same. They have exactly the same mass. Okay. And here is the kinetic energy. So basically, x11 is the x direction of the first particle. x12 is the y direction position of the first particle, and x13 is the z direction. Okay. So the particles can still perform some motion in the x, y, and z. Okay. So there is a dot, there's a square, everything is nice. And in general, I have some potential energy. So this is my kinetic energy. Here is my potential energy. And this is a general function of all the different coordinates of the system. Okay, so here I have to write down x11, x12, x13, x21, x22, x23, and etc., 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 till xn3. Okay, so it's a huge function of all the different coordinates of the system. Okay, now I don't want to count over j and over I, so let's write down different coordinates. Okay, so I will just simply say, let's say that, let's assume x I tilde as a generalized coordinate. Okay. So I don't care if I have first particle in the y direction, fourth particle in the first direction. I don't really care. I just say I have 3n degrees of motion. okay, or 3 degrees of freedom, I'm sorry, and each degree of freedom I'm going to describe as xi tilde. So my Hamiltonian looks like 1/2 m as sum I goes from 1 to 3n xi tilde dot squared plus the potential of u x1 tilde, x2 tilde, x3 tilde, x4 tilde, etc., 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 etc. Great. Okay, so well, I haven't done anything so far. The next step is to say, well, yeah, it's a general function, of course, of all the different coordinates inside the system, but I want to expand this behavior around some equilibrium or some stable point, right? So we assume that there is a stable point for everything. Okay, so this particle is oscillating around some specific fixed point, and this particle is oscillating around some other fixed point, and this particle is oscillating around some specific fixed point, and I want to look on the oscillations around the fixed points. Okay. So in general, it's very complex, and I cannot continue from this description anywhere else unless I assume something. And my assumption is let's look on not so large fluctuations of the system around the fixed point, around the stable positions of all the different particles. Okay, so what do? I basically say, well, xi, it's xi 0 tilde, this is my fixed position, plus this small fluctuation. I'm not assuming that this additional fluctuation is large. Okay. So I'm sorry. Saying the following. So xi tilde plus equals to zeta I. So this is the small fluctuation that I have inside the system. Or let's write down it's the other way around. Plus this. Okay. So all those zetas are my small fluctuations around fixed points. Okay. I assume that there is some sort of an equilibrium with fixed position of all different particles, and I'm looking on the fluctuations around this fixed position, and those positions are described, those fluctuations are described by these zetas. Okay. Okay, since here I have a first derivative, I don't care about this fixed position, so 1/2 m sum I goes from 1 to 3n of xi tilde dot squared equals simply to 1/2 m a sum I goes from 1 to 3n of zeta I dot squared. Okay, great. This is nice. I just expanded my kinetic energy in terms of xi tilde, and I'm doing it right in terms of zeta. And now I'm looking on the expansion of this potential energy. So I'm saying that the potential energy is some constant. What is the constant? The value of the potential energy is in all the fixed positions. Now, since it's a stable point, the first derivative is going down. Okay, so u, it is u at xi 0, x1 0, and x2 0, etc., 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 xn or 3n 0. It's just a constant, plus a sum I goes from 1 to n of du to d z to d xi, right, tilde, computed at xi tilde 0, multiplied by zeta I. Sorry? 3n, yeah. Okay. So this is the first order expansion of my potential energy. It's a constant plus a fifth derivative. I have 3n different coordinates, so I have to take derivative with respect of each of those coordinates. But I'm assuming that this is an equilibrium and stable point. Basically, those are local minimas of all the coordinates. Basically, this guy equals 0. Okay. So I'm going to the next order expansion. Right? What happens in the next order expansion? I have plus 1/2 sigma I goes from 1 to 3n. Sigma j goes from 1 to 3n. du dxi dxj computed at xi tilde equals xi tilde 0 and xj tilde equals to xj tilde 0 multiplied by zeta I, zeta j. Okay. So it's just a Taylor expansion around some local minima, okay, up to a second order. I wish I can continue this, right, to the third order derivatives, fourth order derivatives, but you have already done all those expansions in Mathematics 101, Mathematics for Physicists. Because you have double derivative. With respect to what? With respect to what? No, I have to take double derivatives. Go back to Mathematics for Physics 101. Okay, so if you have two variables, you have to take mixed derivatives. That's how the Taylor expansion works. All right, so I don't have this guy. Look, my point is that the Hamiltonian it equals to the kinetic energy, a constant, and something which is constant values, coefficients, multiplied by zeta I, zeta j. Now, instead of writing all of this with a lot of sums, I'm saying, well, let's try and represent it in a vector form. So zeta vector, it is zeta 1, zeta 2, zeta 3, zeta 4, etc., etc., etc. You know what? It's a row. So it's zeta 1, zeta 2, zeta 3, zeta 3n. So when I have a vector form, the kinetic energy looks like 1/2 m zeta dot transpose. Okay? This is the kinetic energy. This guy, okay, this guy, if I'm trying to write it down in terms of zeta, so it's 1/2 zeta, a matrix A, zeta transpose. What is a matrix A? Aij equals to du dxi tilde dxj tilde. Yes.
גם אני לא הבנתי מאיפה חזר ה-xj אם עברנו לעבוד במימד אחד.
No, we are not working in one dimension. We're working in 3n dimensions. This is a Taylor expansion of a function that depends on 3n variables. Okay? Not everything is one-dimensional. Most of the stuff in our life is 3-dimensional, and the Taylor expansion have mixed derivatives. Yes?
Why is equal to 0?
Sorry? So where I'm taking the derivatives? At the equilibrium points.
No,
Why of this?
Yes.
Because I'm assuming that I'm making all this expansion around equilibrium, and in equilibrium, the potential energy has to be at minimum. Okay? Okay, so my full energy now is 1/2 m zeta dot transpose plus u0, which is a constant. This is u0 plus 1/2 zeta A zeta transpose. I'm now writing it in vector and tensor representation. Because if you wish, this matrix is some sort of a tensor for me. Okay, so the next thing to do is to say, well, A is some general function, right? I wrote, not function, I'm sorry, a matrix. So I want to write down this matrix because it's symmetric. Notice that I don't care if I take first the derivative with respect to j and later with respect to I, or first with respect to I and then with respect to j, because I'm assuming that u is some sort of a continuous function. Now, due to the symmetry, I can write down this matrix A in the following way. So it is S D S minus 1. D, it's a diagonal matrix. S, the matrix of eigenvectors of A. Okay? So our Hamiltonian now don't have any sums in it. Right. It has the following representation. It's 1/2 m zeta dot transpose plus 1/2 zeta s d s minus 1 z transpose. Okay.
Where did your office go?
Sorry?
Where did your office go?
Do I care if I have u0 or not? It's a constant. I can always check my energy such that this u0 is constant, so I completely don't care about it. It can be 0 or it can be some specific value, but as long as it's a constant, it's not going to affect any equations of motions, right? Because as you learn from analytical mechanics, it's just derivatives, some specific derivatives of Hamiltonian with respect to different generalized coordinates. Those are the equations of motions. u0 is not affecting anything. Okay? So I don't care if it's there or if it's not.
And another question?
Yes.
למה אתה בטוח שאתה יכול לחסל?
Because it's a symmetric function. Okay? Due to the symmetry of Aij. Okay? So, and I don't care if I take what is the order of the derivatives. This means that A is symmetric. This means I can use this representation. Okay, now, a nice thing about this guy is that S minus 1 zeta transpose equals to S transpose zeta transpose. Right? Because it's eigenvectors. Therefore, it is.
Explain that again. Why are you assuming S is a unitary matrix?
Why? Because there is always a representation of, you learn it in linear algebra, there's always such a representation for any symmetric Mach function.
You're choosing S to be...
I can choose. I can use this representation. Okay? I don't know what is the diagonals of D. I know that if I pick up S as a matrix that is combined out of eigenvectors, such representation exists. This is why you have this class of linear algebra. You proved it. Okay, so this guy is just zeta S transpose. Okay. So now look what we have. The Hamiltonian is 1/2 m zeta dot transpose plus 1/2 zeta S d zeta S transpose. The nice thing about it is that D, right, it's a diagonal matrix. Okay, now I will do the following thing. I will put inside this guy s minus 1. So let's concentrate just on this guy. So it is 1/2 m zeta s minus 1 is just the diagonal matrix. It's an identity matrix, s multiplied by s minus 1, zeta dot transpose. As here, I had s minus 1 equals to st zeta t. I will say this guy equals to 1/2 zeta s st zeta dot transpose. And this equals to 1/2 m zeta s multiplied by zeta s transpose. Dot. Since S is a constant matrix which depends on basically those derivatives at very specific locations, okay? So S is a constant, so I can take the dot not just with respect to zeta, but I'm taking the dot with respect to this whole vector. It's a vector multiplied by a matrix, so this is still a vector. Okay? Now, overall, what I got is that H equals to 1/2 m zeta s zeta s transpose plus 1/2 zeta s d diagonal matrix zeta s transpose. Dot over here. Thank you very much.
No, not
Oh, here also dot. Here also dot.
Is in both of them dot or just in one of them?
On the multiplicative term. Okay. Why? Because s is a constant. Since s is a constant, I can take a dot on each, and not just on the vector zeta, but on the vector zeta multiplied by s. Think of s as a constant. That's it. Why I have done this? Well, if you look on this and you say, well, Stas, you managed to diagonalize everything, and now it is indeed a bunch of harmonic oscillators, right? So let's look on this zeta s equals to a vector z, okay, where z1, z2 up to z3n. Okay. If I'm using this z vector, and well, it helped me a lot in diagonalize everything, but in order to show to you what actually I have got, I'll go back to the summation representation, and I have the following form of the Hamiltonian. The Hamiltonian now is 1/2 m, a sum I goes from 1 to 3n, zi dot squared, okay, plus 1/2 m, no, I'm sorry, I don't have m, 1/2, a sum, a single sum, instead of a double sum, a single sum. Why do I have a single sum? Because D is diagonal. Because D is diagonal. So I goes from 1 to 3n, di zi squared. Well, I can add this u0 over here. I don't care about this u0, it's a constant. So what is this? It may be harder to see it's from this vector notation, but over here I have 3n independent coordinates because this is the kinetic energy. This is the potential energy. This is a potential energy of 3n harmonic oscillators, right? So what is the energy of a single harmonic oscillator? It's 1/2 z squared plus 1/2 a constant. You can write it down as omega squared if you like, z squared. This is an energy of a single harmonic oscillator. Now here I have 3n independent harmonic oscillators. Okay? What it actually means, it means that indeed any system of 3n of n particles that are somehow interacting with each other, when I'm making an expansion around the minima, around the equilibrium values of all the different positions of all the different particles, I can obtain a picture where everything is independent, where indeed I have 3n degrees of motion which are independent. All those 3n degrees of motions are harmonic oscillators. So Einstein was right in some perspective. There is indeed 3n independent degrees of motion, but he was absolutely wrong in two other things. First of all,
The omega is not the same.
di, which is the omega, is not the same. So the different frequencies of oscillations of all the different harmonic oscillators are not identical. This is point number one. Point number two, which is actually more important, it's not the positions of the particles that are independent. Not the positions of the different particles. Z's are not positions. Z, what is Z? So Z, it's a vector, which I remind you, it is some zeta multiplied by S, and S is an eigenvector matrix of this big derivative of this huge harmonic, not harmonic, general potential function U. These are not positions. They are linear combinations of positions of many particles. Okay? And this is crucial. I don't have independent particles. I have independent Z's. And independent Z's is something different than a particle. I can call it quasi-particles. I will call them phonons. Okay? I will have a name for them. So Z's, my Z's, are phonons. The independent coordinates Z effectively describe positions of independent, not particles, particles with rotations, particles, quasi-particles. And I have a name for them, not me, but Ibai and people that follow him call them phonons. Basically, independent oscillations inside the material. So it's not the particles that oscillate independently, are the different coordinates, generalized coordinates, which are linear function of the original coordinates, but the linear coefficients, I don't have a way to find them. They are independent. So the starting point is not full independence of everything, because, well, then I know how to apply statistical physics. The Pai says, well, it's a great idea to apply statistical physics. It's a great idea to assume that each degree of motion have a specific quantas of energies, like Einstein assumed. You have to make modifications. And the modifications are the particles are not identical. They have different frequencies of oscillations. They are not particles, they are phonons. And it's a very, very important point. Okay. So the next thing that Debye said is, well, I'm going to use those ideas with Einstein, but with some small modifications. Okay. But with some small modifications, which will include different omegas. Okay. I will treat each state differently, and I will count all the different omegas that I have inside my system. Okay. The problem is, well, in order to find those omegas or di's, you have to take this huge function u, take its second derivatives, make the matrix, okay, diagonalize this matrix, and find all the eigenvectors. And then when you have all the eigenvectors, you push it inside over here, you find all the local stability points, you push it over here, and there you go. It's impossible. Okay? This is why Einstein haven't done it, because it's actually impossible. It's too huge. It's not a 2 by 2 matrix. It's 3n by 3n. Okay, what is 3n by 3n? N is even not 1000, right? It's a huge number. So what Debye said? Debye said a very, very nice and interesting thing.
Can I ask a question?
Yes, of course.
Can you measure the phonons in a lab?
Yes.
So
So it's oscillations.
why are you calling them a quasi-particle if you can measure them?
Because it's not a particle.
In what sense it's not a particle? You
It's
can
not a
measure
particle. It has a mass.
The photon doesn't have a mass.
And photon is very localized. Phonon is not. Okay? I can say, here is a phonon. Okay, here is a phonon. Photon, I'm sorry. Here is a photon. Right? And it hits exactly at this point on my screen. Phonon, it's from here. It's a linear sum of different positions of different particles. So where it's located?
Everywhere.
Everywhere, in some sense, right? Okay, it's a wave.
Yeah.
Okay? And it's not localized. This is why it's quasi-particle. This is ideal physics of making a mathematical representation that looks like we have a single particle, but we don't. And then we call this, whatever we formatted, as a quasi-particle. Okay? It's a very nice idea. It's based on mathematical representation of whatever you have inside your system. Okay, so what was the genius idea of Debye of how to find all the different di's? Because I can say, well, 3n is 3n, but what are the different di's? Okay? What are the different di's? And Debye said the following thing. Well, what are the oscillations? Right? So we have phonons. Right? Now, phonons are some oscillations inside the particle. So what kind of oscillations? If I take a string, we have a one-dimensional string. Let's assume that my solid is a one-dimensional line. Okay? And I'm looking for all the different di's that I have inside my system. Okay. Debye said the following thing. What are the different di's? The different di's are the different oscillations that can survive inside my particle, inside my system. Okay. So basically, all the different di's are somehow related to the different wave vectors of standing waves, right? Because what I'm describing to you, I'm describing quasi-particles that are phonons, some oscillations that do not die out. Because if it dies out, it's not representing the general positions or general oscillations inside the system. So I need to focus only on standing waves, waves that are surviving inside my system. So Debye said the following thing. He says, well, I can count the number of standing waves that I have inside my system, right? Because I know that lambda over 2 multiplied by some number n have to be equals to L. Right? So n is an integer. has to be an integer, and this constrains lambda. Okay. So the guy said, well, I have some sort of a condition, because how I'm going to find all the different di's, I'm going to find all the different states or all the different standing waves that I have inside my system. The moment that I know how many standing waves I have inside my system, I know what are the different di's under specific assumptions I have inside my system. So I don't need to solve and find all the different eigenvectors and eigenvalues of a huge matrix. I'm going to use my physical perspective. Those are independent phonons. Phonons represent waves, waves that survive inside my system. Surviving waves are standing waves. I know how to count standing waves because there is a boundary condition. It's like in quantum mechanics. Where all this discretization comes in quantum mechanics? Boundary conditions. Here I can count the number of omegas due to boundary conditions, and I will have some specific number. Okay? And there I go. So we will continue this tomorrow. Thank you very much.
להבין באיזה מובן הם לא אמיתיים.
הם אמיתיים? הם אמיתיים, אבל זה לא חלקיק. זה החלקיק הזה.
אבל אני יכול להגיד אותו דבר על... כאילו גם...
אני יכול להגיד לך שזה x1, 2x1 פלוס x3. יש שם משהו? נניח, אני פתרתי את זה, כן?